So at this point, we want to start looking at capacitance. And I'm going to do something a little bit different and work through some of the PowerPoints as they are, which are drawn from the text, and elucidate and do some examples along the way. And so the first thing to note, okay, what is capacitance? Right, capacitance at the end of the day. Capacitance is a device that stores charge. Okay, that is the fundamental purpose of building a capacitor. It is a device that stores charge. Now, when you build such a device, and the simplest device that you can build are two conducting plates. Okay, and they need to be conductive because when you connect them to a voltage source, they have to be able to allow charges to move freely. So you connect two conducting plates to the ends of a voltage source like a battery, and charge will flow from one plate to the other. Okay, now in a capacitor as shown, right? In a capacitor as shown, this process is nearly instantaneous. So because voltage at its root is potential energy per unit charge, you can think of voltage as a measure of the available energy, electric energy in a system, if you know how much charge there is. So you can move charge from one plate to the other via the battery. So what happens is, this is a simplified picture. Okay, this is a simplified picture, but what happens is when you connect the positive terminal to a conducting plate that's initially neutral, it has initially, for every positive charge on the plate, there's a negative charge on the plate. But when you connect the conducting plate to the battery, the negative charge is attracted to the positive terminal, and so the negative charge wants to flow through the terminals of the battery, and then the battery expels them and deposits them on the other plate. So that leaves your plates equally positive and negatively charged. Okay? So this process happens nearly instantaneously. And as shown, if you have two parallel plates and they're separated by a distance d and there's nothing in between them, sometimes this is called a vacuum capacitor. And when you put an insulating material in between your conducting plates, okay, this is sometimes called an insulating capacitor. And when you put an insulating material in between your capacitive plates, this is often known as a dielectric. Okay, so your insulating material is called a dielectric. And we'll see why dielectrics are important here shortly. Okay, but one thing to note, the simplest situation here is when you have a vacuum capacitor and your plates are both the same size, same thickness, and if they're the same size and same thickness, then they both have the same area A. Okay, so the area A applies to this plate and it applies to this plate. Okay, so your area A applies to both plates. And the basic definition of let me finish this one thought. Capacitance is a geometric quantity. If you have a parallel plate capacitor like this, and you know the geometry of the system, the area on the plates and their separation d, and if you know whether it has a dielectric in between it or not, you can specify what the capacitance of that system is. Or, alternatively, what you're specifying is the amount of charge that the system can store. Okay? Now, capacitance is a geometric quantity. It is a constant for a given situation or a given device, right? If you're not changing the physical characteristics of the device, it will have the same capacitance. The definition mathematically and why we use capacitors in circuit components is that the definition of capacitance is equal to the ratio of the charge that is ultimately deposited on both plates divided by the voltage of the source holding those plates at the potential. Okay? So capacitance is a geometric quantity, and what that means is for a given situation, this is constant. Right? So what that means is, as you adjust your voltage, you will adjust the amount of charge on the plates. As you adjust your voltage, you will adjust the amount of charge on your plates. That's what this equation is telling you. Okay? So C is equal to Q over V. If you have a parallel plate capacitor, okay, then the value of capacitance is equal to epsilon naught A over D. Okay? And if you have a dielectric material, that formula is slightly modified. But for our purposes, for the moment, we will stick with a vacuum being between both plates. So you can calculate the capacitance if you know the geometry, the area and the separation. Now remember, from the first chapter in the textbook that we looked at, epsilon naught was given the value 8.85 times 10 to the negative 12. Okay? And what units did epsilon naught get? Right? What units did epsilon naught get? Well, we can find that out relatively quickly, and this is how you would do it if you don't remember off the top of your head. And I'm not going to require you to remember off the top of your head, but you should be able to work through the following logic. So remember that Coulomb's law is equal to Ke Q1 Q2 over R squared, and F has units of newtons. Q has units, the numerator has units of coulombs and coulombs, or coulombs squared, and the denominator has units of meters squared. So the units on Ke are going to be newtons times meters squared per coulomb. But remember that Ke is 1 over 4 pi epsilon naught, and so the units on that are then going to be coulombs squared over newtons times meters squared. Okay, so this is the units on epsilon naught. 1 over 4 pi doesn't get any units, and so the units on epsilon naught are going to be the reciprocal of the units on Coulomb's constant. So epsilon naught gets C squared, Coulomb squared over newtons times meters squared. Okay? And what this number represents, okay, what this number represents is the permittivity of free space. So since this is the permittivity of free space, okay, what that really means is this basically defines how electric fields are able to propagate through space, the strength with which electric fields are able to propagate through free space, through the vacuum. Okay, that's what the permittivity of free space essentially means. And we will run into the permittivity of free space later when we talk about light. And so we will use it extensively from a theoretical standpoint in a few chapters. Right. Now, why are parallel plate capacitors preferred as the descriptor for introductory physics? One of the reasons is that when you have uniform charge on separated plates like this, they form a rather uniform electric field between them. Okay? Now, toward the edges, you can get what are known as fringe effects. So as you move toward the edges, your field will bow a little bit, and then a little bit more extreme. But near the center, these effects are extremely negligible, and so we don't really get those fringe effects. All right. So we have a uniform electric field. So from this point on, whenever we talk about a uniform parallel plate capacitor, one of the assumptions you can automatically make is that E is going to be constant. Okay. The electric field between the two plates is going to be more or less constant. And so when you have a capacitor that's charged, or a capacitor where the charges are on both plates, there's two ways to keep the capacitor charged. Number one is to keep it in contact with the battery. Or number two, remove the battery but do not connect the plates. As soon as you connect the plates, let's say you connect the two plates with a wire. So if I connect the two plates with a blue wire anywhere, if I were to connect these two plates with the wire anywhere, then these, actually what really happens is these negative charges, the charges that can move, would flow through the wire and would neutralize both plates. Okay. So since the negative charges are the ones that can actually move, they're going to be the ones that would flow, and they would discharge the capacitor. And this process happens really, 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 really quickly. Okay, so when you connect two plates of a charged capacitor, the discharge is nearly instantaneous. And as we will see in the next chapter, this directly relates to the amount of current flowing between the two plates, and the faster that process happens, the more the current. So when you are working with large parallel plate capacitors, you actually have to be very careful that you don't electrocute yourself. So that being said, most commercial capacitors actually come in this form. Okay, this is the shape that most capacitors come in because they're very economical. You can get a large amount of plate in a smaller amount of area if you wrap it up, so you don't have to build as large components. So if you need, if you're physically limited with space in the circuit that you're building, it is quite convenient to use these wrapped capacitors because they save on space, right? And you're actually also getting a few other benefits as well, but we won't worry ourselves with that. But these are what some capacitors look like, okay? And usually this one and this one are going to be classic wrapped capacitors, okay? This one may be an actual parallel plate. I'm not 100% sure what this one would look like if you opened it up. But generally they're not going to be just flat parallel plates, and almost every commercial capacitor is also going to have a dielectric, and we'll see why here shortly. But for the moment we will stick with the uniform vacuum capacitor. Okay, so as we've already mentioned, the capacitance on a system is equal to the permittivity of free space times the area divided by the distance, but this also equals the amount of charge on the plates divided by the voltage. Okay, and so you can use this equation. Okay, you can use this equation to determine several different scenarios. For example, if you're given the voltage and the charge and the area, you can solve for the distance between the plates. If you're given the voltage and the charge and the distance, you can solve for the area, and so on, right? You can be given the voltage, the area, and the distance, and you can solve for the charge and whatnot. One more striking thing about these is if I rearrange this equation. Okay? If I treat my voltage as an independent variable and my charge as my dependent variable, so I adjust the amount of voltage my battery is putting out, and I measure as a result the amount of charge on the plates, the equation that would govern that would look like this. Okay? So Q is equal to CV. But remember that C is a constant. So this has the form of Y equals mx. So if I make a plot of my voltage in volts and a plot of my charge in coulombs, this should be a linear line. Okay? And by definition, this doesn't have an intercept, so it should always start at 0. Okay? The only thing that's going to be different is the slope. How does your amount of charge change? How does your amount of charge change per voltage? That is going to be the slope. And the slope is equal to the capacitance. So if you can generate a Q versus V plot, then you can get the capacitance on your device. Okay? So, with all of that in mind, there are a few other shapes of capacitor that you can conceivably build. One of the more popular from a higher theoretical point of view, because there's some really interesting things that happen here, would be the double shell capacitor or the spherical capacitor. Okay, so you have two conducting spheres, and one sphere is suspended inside the second sphere. And so you put an amount of charge on your inner sphere, and you subtract the exact same amount of charge from your outer sphere. And when I say add charge and subtract charge, I'm talking about positive charge, right? So you add positive charge to the inner sphere, you subtract positive charge from the outer sphere, and you're left with an inner positively charged sphere and a negatively outer charged sphere. And depending on the distance between the two surfaces, you can calculate the capacitance of this system. And it's rather easy to do, but we won't do that here because we simply don't need to go to that level. But just so you guys are aware that this is a system that if you're going into electrical engineering, you will see this system in the future. Okay, if you're going into electrical engineering or if you're going into physics, you will see this in your upper level electrodynamics courses. Right, and similarly, we also have the cylindrical capacitor. And if you'll notice, okay, especially from Gauss's law, parallel plates, spheres, and cylinders kind of harken back to Gauss's law. And that's no accident because these systems are highly symmetric. Okay, these systems are highly symmetric. One way that you can get variable capacitance is if you have a knob with different sized plates that you can put in your system and connect to your voltage leads, then you can get variable capacitance. So you can select the amount of capacitance you want your system to have. Okay? Okay. Now, for the fun stuff, right? For the fun stuff. what happens when you put capacitors in series or parallel? Okay, so first of all, we need to define these terms and also note, okay, that the circuit diagram symbol for a capacitor is most often going to be just two parallel plates. Okay, as we move forward into circuits and circuit diagrams, you'll see that batteries are often related by a series of alternating large and small lines. And batteries are denoted by alternating large and small lines. So that's just a note as we go forward. But this is what is known as a series connection. Okay, and this will hold when we talk about resistors as well. So a series connection simply means when you have one single loop that your charge moves through. As your charge moves through the battery terminals, there's only one single loop. And what is true, so let's see. So if we define the negative charge as the things that are moving, when these plates were neutral, right? When these plates were neutral, you flip a switch and to connect the wires to the battery terminals, and the negative charges would flow this way and be expelled this way and be deposited on this negative plate. So you leave this plate with a plus Q and this plate with a negative Q, but then because everything is conducting in between, this negative charge will repel the negative charges off this plate, and those negative charges will be deposited on this plate. You'll have positive charges on this plate, and the negative charges repel the negative charges from this plate, so you're left with a positive plate, and they're deposited, the negative charges are deposited on this plate. So the process just essentially is kind of like symmetric around everything. But you have just one loop. The charge will flow through the circuit like this. Okay, you just have one single loop. And once the plates are charged, nothing happens anymore. Okay, and again, without anything else in the circuit, this is really fairly instantaneous. Okay, this is a really instantaneous process. So how do we analyze the capacitors that are in series? So let's look at this in a little bit of detail. To start, we'll just talk about two capacitors. So if I have a battery, and let's actually move this up because I'll use the space to draw. So if I have a battery and two capacitors, for the moment I'll just label them generically C1 and C2. And we have a voltage V across our battery. Okay. We've already established that the total amount of Q's on the plates are going to be the same. Okay. The total amount of Q's on the plates are going to be the same. And I should have specified something from the beginning. And that is, in this formula, C is equal to Q over V. Q is the magnitude of the charges on one of the plates. Not the total plus Q magnitude plus the negative Q magnitude, but it's just the magnitude of the charge that was moved. Okay, so you moved an amount of negative charge Q off the positive plate deposited on here, and you left plus Q. So Q here is the magnitude of the charge that was moved. And so when you come down here into the parallel or the series case, okay, you've still only moved an amount of charge Q. Okay, so Q is the same for both capacitors. Now, why would you do something like this? Why would you connect two capacitors in a formation like this? The answer is if you need a specific amount of capacitance and you don't have that capacitor. Okay? If you need a specific amount of capacitance and you don't have that capacitor. So, what you can do is arrange two capacitors to have an effective or an equivalent capacitance. So, these two capacitors connected in series are going to have an equivalent capacitance. Okay? And we know that the equivalent capacitance of the entire series is going to be just the total charge that was moved divided by the voltage of the battery. This is the same thing as saying I have a single capacitor and I would still move the same amount of charge, but the equivalent capacitance is going to be different than either of the two individual capacitors. Okay. Now, there's one more thing I should actually mention before finishing that example, and that is the units on capacitance. So the units of a capacitor are called the farad. Okay, the units on the capacitor are called the farad. And so since C is equal to Q over V, 1 farad is equal to 1 Coulomb of charge per 1 volt. So if you had a capacitor of 1 farad in capacitance, what that means is a battery of 1 volt could move 1 Coulomb of charge between the two plates. That is an extremely high number. Okay, that is an extremely high number. So most capacitors are usually measured in things like picofarads, femtofarads, and this is 10 to the negative 12 farads. This is 10 to the negative 15th farads. We also have nanofarads, microfarads, and millifarads. These are the most common that you would use. Okay. But just be aware that the farad is the equivalent of a Coulomb per unit volt. All right. And so, with farads being equivalent to a Coulomb per unit volt, whatever the value of my capacitors are, I can also apply the rule for capacitors to each individual capacitor themselves. Since voltage is a way to measure energy per unit charge, what that means is this is the total energy in the system, and that energy must be distributed between C1 and C2 with individual voltages V1 and V2, and energy conservation demands the energy put into the system by the battery. The energy can't disappear, so it has to appear across the capacitors. So what we would say also in the series case is that the total voltage of the battery is equal to the sum of the voltages across the individual capacitors. And therefore, we have the relations that C1 is equal to the charge that was moved divided by V1, and C2 is equal to the charges that were moved divided by V2. Okay? And so, because this equation holds, I can solve my capacitance equations for voltage, And I can say that the voltage relating to the total equivalent circuit is going to be equal to the charge that was moved divided by the equivalent capacitance. And V1 is going to be equal to Q over C1. And V2 is going to equal Q over C2. And so what that means is if this equation is true, then we're going to have Q over C equivalent is equal to Q over C1 plus Q over C2. Now, if I add more and more capacitors in series, this formula would just go on. Q over the capacitance of that specific capacitor. But you'll notice that because the charges were the same, like we just argued, these cancel out. And I'm left with 1 over the equivalent capacitor, or 1 over the equivalent capacitance is equal to 1 over the first capacitor plus 1 over the second capacitor. So, to get the equivalent capacitance, what we want to do is get common denominators here and then invert both sides. So what we mean by that is this. Okay? We have 1 over C equivalent equals 1 over C1 plus 1 over C2. And getting common denominators, this is C2 over C1 C2 plus C1 over C1 C2. And so then this becomes C2 plus C1 over C1 C2 is equal to 1 over the equivalent resistance, or capacitance. And so the equivalent capacitance in series is going to be equal to C1 C2 over C1 plus C2. Now, when you have more than 3, I would use a computer, okay? But when you have 2, you can get away with this. If you have 3, you can derive a formula, but it's a little bit more complicated than this, right? It's a little bit more complicated than this. But just as a few examples, okay, what happens when the capacitors are equal? The individual capacitors are equal. What happens in that case? Well, in that case, the equivalent capacitance is going to be equal. If these are equal, I can drop the subscripts, and I just have C squared over 2C. And that C is going to cancel with one of those, and I'm going to get C over 2. So when I have identical capacitors, the effective total capacitance is actually reduced. And that is a feature in series capacitors. When I have series capacitors, the overall capacitance of the entire system is reduced. Okay? And as another example, what happens when they're extreme differences? So one might be much larger than the other. Okay? What if C1 is much, much larger than C2? Right? To a good approximation, if that's the case, then I still have C1, C2, but the sum in the denominator, if C1 is much, 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 much larger than C2, then the sum is effectively equivalent to C1, right? It's the equivalent of if C1 is, say, 1,000,000 times bigger than C2, if you have like a microfarad and a picofarad capacitor, one of them is going to be much, 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 much larger. So when you add the really small one, it doesn't hardly contribute anything. And that means that the C1s cancel out and I'm just left with C2. So the larger you make your difference between the two capacitors used, you will approach the total equivalent capacitance of the system being equal to the smaller capacitor. Okay? So now let's actually throw some numbers in here just for example's sake. And we'll use numbers that are not so widely disparate, nor equal. So we'll see an example of how to do this. So what if I have a battery of 12 volts and I have a capacitor of let's say this capacitor is 12 micro, we can use microfarads, it doesn't matter. And let's say this one is 24 microfarads. Okay, so from the, and I want to know what the equivalent capacitance is, and I want to calculate the amount of charge on the plates. Okay, so my equivalent capacitance can be found from this general formula. So my equivalent capacitance is going to be 12 times 24 over 12 plus 24, right? And this is going to be in microfarads at the end of the day because the numerator is in microfarads squared, the denominator is in microfarads, so your overall result is still going to be in microfarads, which it should be. And when you do this, when you have nice numbers like this, there's a few tricks you can do. Okay, there's a few tricks you can do. You can realize that 12 is a common factor everywhere. And so this is the same thing as saying 12 times 1 times 2. And this is the same thing as 12, 1 plus 2. Okay? And when you do that, you can cancel out your 12s, and this turns into 2/3. Okay, so 2/3 of a microfarad, right? 2/3 of a give me just a second, make sure that that is correct. And ignore exactly that statement. This is still 12 times 24. Something didn't feel right. So this is 12 times 24, but you can still factor the 12 out of the denominator, and so your 12s do cancel out, and then this is 24 divided by 3, or 8 microfarads. Okay. So you have 8 microfarads for the equivalent capacitance. How much charge? Well, because Q is equal to C equivalent times V, this is 8 microfarads times 12 volts. And 8 times 12, if I'm not mistaken, is 96. And farads times volts is coulombs, so microfarads times volts is microcoulombs. So I would have moved 96 microcoulombs of charge between the two plates. Okay. Now, there's another way that I can arrange plates, and this is called in series, or in parallel. Okay. So this is parallel. And here, instead of the total value of the voltages across all the capacitors adding up to the total voltage of the battery, what you're effectively doing is connecting each capacitor to the battery. So here the voltages that each capacitor feels is going to be the same. So in the previous example, the charge was the same, but the voltages were different because the capacitors were different. Here, the voltages are going to be the same, and the charges are going to be different because the capacitors are going to be different. So another way of drawing this that might be a little informative would be to look at something like this. So if I have a battery and I have one capacitor, and then I also connect another capacitor to the battery like this. So what's happening is the voltage between these 2 points is the same voltage as the battery. So the second capacitor, C2, is feeling the exact same potential difference that the first capacitor is. And so what that means is there will be plus Q1 and minus Q1 and plus Q2 and minus Q2 charges on the plates. Okay? And so, with that in mind, the equivalent capacitor, if I were to view this combination as a single capacitor, it would have a total amount of charge that was moved divided by the voltage of the battery. But in this case, the values of the charge add up. The battery drew an amount of charge Q1 off of the positive plate and deposited it onto the negative plate. And it drew an amount of charge Q2 on the second plate. And so, what that means is, here in the parallel case, Q total is equal to Q1 plus Q2. Okay? Q total is equal to Q1 plus Q2. And again, the individual rules for capacitors apply to each individual one. And so, what I do is I solve both systems for the total charge, because I know that Q total must equal Q1 plus Q2. But Q total is equal to the equivalent capacitance times the voltage. And by the same token, both of the other two are going to follow the exact same pattern. So this is going to be C equivalent times V. And this is going to be C1V plus C2V. But the values of the voltage are all the same, so they all cancel out. And the equivalent capacitance is therefore just the sum of your individual capacitors. And so if I added a third capacitor in here, it would just simply extend this formula. Okay? So if you wanted to talk about, a system with two capacitors in parallel and put numbers to this, let's just again make this 12 volts. I like 12 volts, so I'll use that a lot. And let's use the same numbers that we had before. This is 12 microfarads, and let's let this be 24 microfarads. So in this case, this is going to be 36 microfarads. Okay? This is going to be 36 microfarads. And the total amount of charge that the battery moved between both plates is equivalent to the equivalent capacitance times the voltage. So this would be 36 microfarads times 12 volts. and 36 times 12. If we do that in a calculator, 432. So this is equivalent to 432 microfarads. Okay? So we will pause there for this video, and then we will look at more exotic examples next time and talk about energy and energy density with capacitors. So thanks for hanging with us, and we will see you in the next lecture.